In this video, we'll be discussing rates of change in the natural and social sciences. Something to remember from Chapter 2, you have what is called the average rate of change and the instantaneous rate of change. The average rate of change is when you take 2 points and you basically use the slope formula. So the change in y, delta y, over the change in x is going to give you the average rate of change. The instantaneous is when you take this point and you make it become very, very close to the other point. The closer the x values are to each other, basically the change in x as it goes to 0, meaning as the x values get very, very close to each other, okay, the difference goes to 0, then the change in y over change in x ends up becoming the derivative, the instantaneous rate of change. So remember, whenever a function has a specific interpretation in one of the sciences, its derivatives will have a specific interpretation. What we have discussed so far is dy over dx, which is y with respect to x. But anytime you're in the sciences, you will have specific interpretations. So for example, this would be the area with respect to the radius if you're discussing something that has to do with a circle. Or in this case, you could say that the velocity with respect to time. The derivative is the same. dA over dr is just like dy over dx. So y with respect to x, you're going to have very specific types of interpretations depending on the word problems that we are going to be dealing with. So for example, in physics, let's say you have some particle moving in a straight line. The average velocity is going to be the change in the position over the change in time. The instantaneous velocity is going to be the derivative at that specific point. And then they have what's called the acceleration, which is the instantaneous rate of velocity with respect to time. How fast is it moving at a specific time? And then the acceleration at a specific time. So for example, the position of a particle is given by this function. Find the velocity. Velocity means we need to take the derivative of our function. So the velocity is going to be 3t squared minus 12t plus 9. Now they want to know the velocity after 2 seconds. So you are going to plug into time, and you will get a -3 meters per second. So the velocity is decreasing at this point. After 4 seconds, that means you're going to plug in 4 into time, and you will get 9 meters per second. That is how fast the particle is moving at a specific instant. When is the particle at rest? The particle is at rest when the velocity equals 0. So if we're going to take the velocity, 3t squared minus 12t plus 9, and we will set this equal to 0. So I can factor out a 3, and then I can factor this into 2 parentheses because it is a trinomial that can be factored. So, and I can bring the 3 down, but when I divide everything out by 3, then it goes away. So after 1 second and after 3 seconds, the particle is at rest because you would take each of these and set them equal to 0. Now, continuing on with the same problem, this is the graph of this function. So if you think about it, why is the velocity 0 at 1 and at 3? Because at 1, you end up having a horizontal slope, and at 3, you end up having a horizontal slope. So what's happening is this particle is moving away from its starting position up to 4 meters, and at 4 meters, it turns and starts moving back towards its starting position, back home, And then at 3 seconds, it actually turns back and starts moving away from its starting position forever. So part E says find the total distance traveled. Well, we know that from the starting position up to 1 second, it moved 4 meters. 4 meters because you can look at the graph, or you can plug in the distance from 0 to 1 and you'll be able to get what the distance would be. And then from 1 second to 3 seconds, it went back from 4 meters back down to 0 meters, back to its starting position. And so again, it went 4 meters. And then from 3 seconds to 5 seconds, because it wanted to know during the first 5 seconds, it went from 0 up to 24. So if you were to add these distances together, you would get 32 meters total that it traveled. And then next, find the acceleration after 4 seconds. That means we need to take the velocity, which we know is 3t squared minus 12t plus 9. And then we need to take the acceleration, which is the derivative of this, which would be 6t minus 12. And we want to know at 4 seconds. And we will get 12 meters per second squared of that. Now, going back to the total distance, you can do this algebraically if you did not graph it. Graphing it, you can be able to see how far away from its starting position it went, back to it, and then back again. You can go ahead and take the distance from that, though, at the same time to be able to subtract. You would take the distance from 1 to the distance at 3 and subtract those numbers. Same thing, the distance from 3 to the distance of 5. So if you plugged 0 into the function and then plugged 1 into the function, subtract those numbers and you would get your answer. Like if you plug in 0, you would get 0. And if you plug in 1, you would get 4. And so that's why you would get 4. And you would just subtract. Something else with physics, if a rod is homogeneous, then its linear density is constant throughout. Meaning, let's say you had a rod that was homogeneous. That means the rod had the same density all the way throughout the entire rod. Some rods are not homogeneous. For example, some rods might actually be thicker at the ends than in the middle, or it could be thicker in the middle than at the ends. That would not be homogeneous. But if it is homogeneous, that means, for example, let's say you had a 40-pound rod and it was 10 feet long, then the rod, you could say the density would be 4 pounds per foot, because every foot you go, it's going to weigh 4 pounds in between each, obviously, those feet. You would just divide the mass, 40 pounds, by the length, 10 feet, and you would get 4 pounds per foot. Or in kilograms per meter, for example, when you're talking about density. So the average density would be the slope formula like we discussed in the past. Now the linear density is the rate of change of mass, which is where you would get the derivative. As the lengths, as you take two different lengths, like let's say you had x of 1 here, and let's say you had x of 2 here. If you can make the second x get closer to the first x, the difference being very close to 0, then you would end up getting the derivative. So let's say a rod is not homogeneous, which means it does not have the same density. And let's say the mass is measured from left to some point in towards the rod. And let's say the mass is actually the function, the square root of x. They want to know the average density, so you're looking for the slope formula, between 1 and 1.2. So you're going to take 1.2 and plug it into the function, and then plug 1 into the function, and then on bottom, you're going to subtract those x values, just like the slope. So I'm going to plug 1.2 into my function, and then I'm going to plug 1 into my function, and then on bottom, I'm going to subtract. And if you do that, you will get 0.477 kilograms per meter. In biology, the number of individuals in the animal or plant population at time t is some type of function. The average rate of growth in that period, again, is the slope like we've been discussing. The instantaneous rate of growth is where it becomes the derivative at an instant, not at a range, but at an instant. So let's suppose that a population doubles every hour. Therefore, you would have the function n of 0, which is the initial population, times 2 raised to the t, where n of o is the initial and t is measured in hours. If the initial population was 100, so I'm going to place 100 in for n of o, n of 0, I will have this function. They want to know the rate of growth at a specific time after 4 hours. So we're going to be doing the derivative of this function. So the derivative of an exponential function, this is just a constant. The derivative to the t is actually going to be a log. So it is going to be the function multiplied by the natural log of the base. And we want to know after 4 hours. So we're going to plug in 4 into t, and we get roughly about 1,109.04 bacteria per hour. If a rock is thrown vertically upward from the surface of Mars with some velocity, then you would have this function represented by that let's say a rock is thrown vertically upward from the surface of Mars with the velocity. The height is going to be represented by this function. What is the velocity after 2 seconds? Well, the velocity is the derivative of the position. So to find the velocity, I'm going to take the derivative, which is 15 minus 1.86 t squared. Nope. Sorry, that's not the derivative. That's the original. Is going to be 3.72 times t. And now I want to know after 2 seconds. So I'm going to plug in 2 for t, and I will get 7.56 meters per second. Now they want to know what is the velocity of the rock when the height has reached 25 meters on its way up. So what it is saying is if you were to graph the position of the rock, it is thrown upward and then it's going to eventually come back down, okay? 25 meters, let's say, is here. So we want to know as it's on its way up, what is the velocity at this point when it reaches 25? So they want to know basically when you take the velocity, they want to know at a certain number of seconds when it's 25 meters up, what is the velocity at that point? Well, to find the velocity at a certain point, you need the x value. So we know the y value at this point is 25, but we need to know what is the x value, or in this case, because it's specifically about a rock, we want to know what is the t value at that point. So what we are going to do is we are going to graph this function. So if you, in y equals, if you're to graph the function, and then I want to know when does it reach 25 feet, or I guess meters in this case. So what I did is I made a horizontal line at 25. And if you graph it, you have the rock graph, and I want to know when does it cross 25 meters on its way up. And why does it say on its way up? Is because it will eventually start coming back down, and it's going to be at 25 meters at another point. We want to know, as it's on its way up, what is the velocity at 25. So what I'm going to do is I'm going to hit second trace. I want to know, where do these two lines intersect? So I want to know, it's going to ask for the first curve, so I'm going to get really close to this intersection point at the first curve, hit enter. I want to get really close to the intersection from the second curve, hit enter. Hit enter one more time, and you will get 2.35. So after 2.35 seconds, the rock will reach 25 meters. So what we're going to do is take the velocity, and we're going to plug in 2.35, and we do that, we will get when we do that, we will get 6.258 meters per second. So after 2.35 seconds, the rock is going 6.25 meters per second. That is how fast that the rock is traveling at that point. Let's say sodium chlorate crystals are easy to grow in the shape of cubes by allowing solution of water in sodium chlorate to evaporate slowly. If the volume of such a cube, or if V is the volume of such a cube, calculate the derivative when the cube is 3 millimeters. So first we need to know the volume of a cube. Well, we know that the volume is length times width times height. And since it's a cube, that means the length, width, and height are all the same value, which is x. So x times x represents x cubed. So to find the derivative of this, then it would be 3x squared. And we want to know at the point when x is 3 millimeters, so we're going to plug in 3, we will get 27 for the change in the volume, I guess, with respect to the change in the length of the length, width, and height. A spherical balloon is being inflated. Find the rate of increase of the surface area. So we're going to find the derivative of the surface areas with respect to the radius, in this case, at the point of 2. So the derivative of 4 pi r squared, well, 4 pi is a constant, and the derivative of r squared is 2r. So the derivative of the surface area is going to be 8 pi r, and we want to know at 2 feet. So we will get 16 pi, or whatever 16 pi is, 50.27 feet per, in this case, we're not sure if it's per second, if it's per minute, if it's per hour, we're not sure, but it would be the feet per whatever time is given to us. A bacteria population doubles every hour and has an initial population of 400. Well, we learned from a few moments ago that this represents the function of a bacteria population doubling every hour. We know that the initial population is 400, so we'll get 400 times 2 to the t, and we want to know the rate of growth after 2.5 hours. Rate of growth means we need to find the derivative of this. So the derivative is 400, that's just a constant, so we're just going to bring it down. And the derivative of 2 to the t is just going to be the function times the natural log of the base, and then we're going to plug in 2.5. So if we plug in 2.5 into this, we will get, we will get 1568.4 bacteria growing per hour.